Hello everyone, we are Group 18. The topic we want to introduce today is the overview of Ethernet technology. So what is Ethernet? Ethernet is a communication protocol standard that allows multiple devices to connect within a local area network. It provides a reliable way for devices to exchange data, supporting data creation, storage, and sharing in both home and enterprise environments. It has become the most widely used LAN technology due to its simplicity, scalability, and cost effectiveness. To make sure different devices can work together in a network, we need a standard. Ethernet is defined by the IEEE 802.3 standard, which was introduced in 1983. In the OSI model, Ethernet can operate mainly at Layer 1 physical layer and Layer 2 the data link layer. At the physical layer, it defines how data is transmitted over cables and connectors. And at data link layer, it takes care of frame formatting, addressing, and access to the shared medium. The data link layer is further divided into two sublayers, MAC and LLC. The MAC sublayer is responsible for the most of the work. Next, I'm going to talk about some relevant technologies of Ethernet, and I will look through Ethernet from these two layers. Let's start with the evolution of Ethernet physical layer standards. Firstly, I will talk about the transmission media. At the very beginning, back to 1980s, Ethernet used thick coaxial cables. These were strong but not easy to install. Then in 1990, twisted pair cables were introduced. They quickly became the standard in most local networks because they were cheaper and easier to handle. And by 1993, fiber optics entered the scheme, allowing for much longer distance and faster speeds. From 1995 to 2002, we saw fiber expand even more, with both single-mode and multi-mode options. In recent years, Ethernet has adapted to new needs. In 2015, single-pair Ethernet was introduced for cars and industrial systems. And from 2020 onward, high-speed optics using POM4 modulation have made 400 and 800 Gbps possible. Alongside the media, Ethernet speed has also grown a lot. At the start, speed was just 10 gigabits per second. This was the first generation. And fast Ethernet increased that to 100 Mbps. Then come the gigabit Ethernet with 1 Gbps, which is still common today. Then gigabit Ethernet follows in the early 2000s, mainly for data centers. After that, we saw high-speed versions like 25, 40, 50, and 100 Gbps. And now we even have ultra-high-speed Ethernet, up to 200, 400, or 800 Gbps, thanks to better encoding and fiber technologies. So in short, Ethernet has grown from a simple office network to a powerful backbone for modern communication. Now I'll talk about signal encoding in Ethernet physical layer. The signal encoding defines how digital bits are represented as discrete electrical waveform for transmission. Over the years, Ethernet has used several encoding methods. Firstly, I will introduce Manchester encoding. It was used in 10BASE-T Ethernet. In this method, each bit has a voltage change in the middle. According to the IEEE 802.3 version, the 0 is encoded as high to low transition, and is a low to high transition. This content mid-bit transition means the signal carries both the data and the timing, so the receiver can stay synchronized without needing a separate clock. But the downward is more bandwidth is needed because every bit creates two level changes. Then is the multi-level transmit 3 encoding. The MLT3 encoding is used in 100 base TX. If the bit is 1, the signal moves to the next level in the sequence, and if the bit is 0, it stays at the current level. This means fewer transitions overall, which makes it better for high-speed transition and reduce electromagnetic interference. It's more efficient than Manchester, but by itself, it doesn't guarantee enough transitions for synchronization. That's where 4B, 5B comes in. 4B, 5B encoding is used together with MLT3 in 100 base TX. It converts every 4 bit of data into a 5-bit code that will avoid long string of 0. These codes are designed so that there are enough transitions in the signal, which helps keep the timing correct when combined with MLT3. It improves signal reliability and keep the receiver in sync. The trade-off is some extra bits, but it's more efficient than Manchester, about 80% coding efficiency. Now let's move on to the data link layer in Ethernet. The main job of this layer is to make sure data is sent reliably over the link. In Ethernet, the data link layer has two parts, the LLC and the MAC. But in practice, most of the time we only care about the MAC sublayer, because that's where all the important stuff happens. The MAC layer handles 4 main things. Firstly, it formats the data into frames so that they can be set over the wire. Second, it adds addresses so that the data goes to the right place. Third, it controls accesses to the medium so that not everyone sends data at the same time. And finally, it checks for errors using a special field called FCS. Here's the structure of a standard Ethernet frame. It starts with a preamble code and start frame delimiter, or SFD. This helps the receiver get ready and line up with the incoming bit. Then we have 2 MAC addresses, the destination and the source. This tells the receiver who the data is from and who is for. Next, come to the type or length field. This either shows the size of the data or tells what kind of data is inside, like IP or ARP. After that, we have the data field. This is actual content being sent. Finally, there's the FCS or frame check sequence. This is a 4-byte code used to detect errors. If there's a mistake in transmission, the receiver can catch it here. Let's now look at the medium access control mechanisms used in Ethernet. It plays a key role in making sure devices can share the network medium property. In half-duplex Ethernet, we use CSMACD, which stands for Carrier Sings Multiple Access with Collision Detection. Here's how it works. For sending, a device listens to check if the network is free. It is called carrier sense. If it's clear, it starts transmitting. But if another device stands at the same time, a collision occurs. The collision is detected and the device stops transmitting. They then wait for a random amount of time before trying again. This system helps avoid long-term conflict and keep the network running. But nowadays, CSMACD is rarely used because modern Ethernet works in full duplex mode. The full duplex Ethernet is what we use in modern network. In this mode, devices have two separate paths, one for sending and one for receiving. That means they can transmit and receive data at the same time with no collisions. Because of this, we don't need CSMA-CD anymore. There's no need to check if the medium is free, and no need to back off after collision. This leads to much better performance. 4-duplex Ethernet allows higher throughput, less delay, and more stable communication.
Next, I will introduce some applications of Ethernet. In modern communication networks, the access network connects the core networks to the users and delivering services like internet, voice, and video. With the rise of high bandwidth applications such as remote work, cloud services, and IoT, fiber access is increasingly adopted to meet demands for higher speed and better stability. So a fiber access network uses optical fiber between the OLT here. OLT means optical line terminal, and ONU, or sometimes we call it ONT, which is optical network unit or terminal. And based on the ONU's location, it can be divided into different types as shown here. And FTTH, which is fiber to the home, is a very typical form where the fiber is deployed directly to the user's home, offering excellent performance. Well, for FTTH, the technical architecture can be divided into two main types, which is AON and PON. AON means active optical network, and PON means passive optical networks. For AON, it is a typical point-to-point architecture shown here, and where each user has a dedicated optical fiber connection, and signal transmission and distribution are handled by the intermediate active devices, such as routers, switches, or aggregators. AON also offers notable advantages in bandwidth capacity and transmission distance, also the data isolation and security. For PON, the passive optical networks, it adopts point to multi-point topology, and well, it uses passive optical splitter to distribute signals from the central OLT to multiple ONU or ONT. Because there are no powered equipment in the distribution path, so that PON can significantly reduces both deployment and maintenance cost, and offering excellent energy efficiency and cost effectiveness. And compared to AON, PON has significant economic benefits and long-term maintenance advantages, so that PON has become the mainstream architecture for our modern FTTH deployments nowadays. And with the development of the PON architecture, multi-standard systems have emerged. Among this standard system, EPON, which is Ethernet Passive Optical Network, and GPON, which is a Gigabit Passive Optical Network, are most widely adopted. For EPON, there are two main types, the 1G EPON and 10G EPON. For 1G EPON, it combines both Ethernet and PON, and it is based on IEEE 802.3AH here. And it uses standard Ethernet frames and a point-to-multipoint fiber network. Also, it uses a single fiber for both upstream and downstream. By using two wavelengths, like I show here for upstream, the wavelength is 1310 nanometers, and for downstream, the wavelength is 1490 nanometer. And for downstream, the data is broadcasted from the OLT to the ONUs, while for the upstream, it uses TDMA with OLT managing time slows via MPCP. And nowadays, as bandwidth needs growing. IEEE also introduced the 10G EPON. 10G EPON is standardized in 2009. It is called IEEE 802.3 AV and is backward compatible and supports both symmetric and asymmetric modes. Also, it is noteworthy that 10G EPON can smoothly upgrade from 1G EPON. It can share the same ODN and can run 1G and 10G system on the same OLT and port. This protects existing investment and supports future high-speed needs. Well, the next mainstream standards for PON is GPON. GPON is a very popular PON standard defined by ITU-T rather than IEEE. And GPON is known for its asymmetric data rates of it can offer 2.4 Gbps per second for downstream and 1.2 Gbps per second for upstream. Well, it also supporting symmetric and asymmetric configurations flexibly. From the perspective of the data transmission here, although GPON can carry Ethernet traffic, it's not actually part of the Ethernet family. Instead, it uses its own format called GEM frame here. It is not a standard Ethernet frame. And what's more, GPON also uses TCONs and dynamic bandwidth allocation to manage bandwidth and ensure quality for different types of services. Well, nowadays in real-world deployment, GPON compared to EPON is given better performance, but EPON is usually cheaper. But still, both are widely used today by operators for FTT networks. For Ethernet, it is not just used in everyday life like FTTH we mentioned before. It also widely adopted in the industrial world, especially control systems. Because Ethernet has very high bandwidth and low cost and excellent scalabilities. In most of the industrial environment, like I shown here, we often face a very large number of devices and heavy data transmission. And at the same time, stabilities, reliabilities, and high-speed performance will be very significant to this industrial environment because it can ensure the plant safety and the efficient production of the plant. So that industrial Ethernet supports gigabit or even faster speed, and with added security features like authentication and access control, it can ensure data confidentiality and integrity. Right now, a wide range of industrial Ethernet are in use, and here the Ether CAT is growing rapidly due to its flexibility and low cost. And well, this Ethernet, this Ether CAT can work in real times by sending a single frame through all the nodes. And the master here will build the frames and send it out. During the each cycle, the frame travels through all devices and return to the master. The frame contains information for each slave and introducing address command types, such as read or write and process data. And also it will then pass through each devices, and that devices will read its own data and ensures new data back to the frame and before passing it on. And once the frame reaches the last node, it will send back to the master using Ethernet for duplex feature. And with Ethernet's advantages, such as low cost and high speed transmission, it is becoming the mainstream choices for the industrial communication. As Industry 4 continues to advance, and increasing number of enterprises are now connecting their devices to cloud platforms, fueling the rapid development of industrial Ethernet. According to statistics showing here, well, you can see that the industrial Ethernet market surpassed 10.5 billion US dollars in 2024, and it projected to maintain an average annual growth rate for over 8% from 2024 to 2032. Also, with this wide range of applications, Ethernet has now been deeply integrated into key industrial sectors such as oil, transportation, and energy, showing in this pie chart. So that it demonstrating that strong market potential and adaptability across the industry of the Ethernet. Overall, Ethernet not only finds widespread use in consumer and industrial settings, but also it plays a very vital role in the scenario presented on these pages here. And since its inception, Ethernet has never ceased to evolve. With continuous technological advancement, we can confidently or expect that in the future, Ethernet will offer high speed, lower latency, and enhance security, and even broader application scenario. And that's all for our presentation. Thanks for listening.